Welcome to Entity System Architecture with Unity. And first of all, I have the most important question to you guys. Who still have hangover? No one? OK, cool. Some people? Nice. Well, it can get really difficult because this talk is really technical, so buckle up and let's start. My name is Maxim, here is Simon. We work for Vuga. And Vuga is Berlin-based game company who's dedicated to make games for Angela Merkel. And also for the rest of the world, actually. So we are really dedicated to make games for everyone. And this is the whole company. But we are not here, we are around 300 people. But we're not here to talk about Vuga, we're here to talk about entity system architecture. And the first question would be actually why, right? Why would we do this? And it's also the most important question to ask all the time if someone presents with something new, right? And to answer this question, we have to be really honest, and we have to admit that we come actually from different backgrounds. We come from Flash development and native iOS development, where when you want to develop games, you don't have direct architectural guidance like you normally have with Unity. So when we did game development in Flash and on mobile, we looked at different architectures, how you can structure your code and your games. And Entity System proved to be really nice. So when we switched to Unity in 2013, roughly, we found out that Unity also is cool, but we had a few pain points. And it's here we listed just the 5 most important ones. And I would like to go through them one by one. Testability. This is an example of a project which I worked on for iOS in Objective-C, where we had a really high code coverage. We actually worked test-driven. So therefore, we had, sorry for German, I only had this slide, like this screenshot in German because the project was like 2013 and I couldn't remake it in English. So we had around 91% test coverage per line. Also, what was interesting is also we had only 8,700 method lines of code for a strategy game. This game was a Clash of Clans type of game, actually. Just curious, who of you guys actually worked on a Clash of Clans type of game? Hands up. Few people. OK, I would expect that looking at the App Store and so on and so forth. So that actually people work on such type of games. And testability was important because it's a simulation game, but it also supported the next point. What we also did was code sharing between client and backend. Because actually, this kind of game is very competitive. So you would like to prevent cheaters, right? And the easiest thing to do is share code. The problem with Unity, if you structure all your code in mono behaviors, is that C# is a very portable language. You can run it on anything, actually. But if you have a dependency to Unity engine, then it becomes really tricky. So therefore, it would be nice to be able to decouple your simulation logic from Unity engine. And this is pretty easy using entity system architecture. Another thing which was kind of a pain point for us is codependent logic. What do I mean by this? Imagine you have here this unit, and it's a game object, and then you have like these things which are also game objects, right? And if you have your AI on the game object, then it's pretty easy to find the next target, right? You just say like, OK, select the closest one. Simple. What happens now? If AI is on every game object, then it's really easy to do that they will all target the same thing. But the problem there, what we actually want to do is something like this, to distribute the units on the target, dependent on your AI, but sometimes it's really important to do something like this. And if you would like to do it with mono behavior, what you would have to do is either send messages from game object to kind of negotiate which one should go where, or you need some kind of a supervisor, which is also possible, but it becomes a little bit more complicated, and we had a really simple solution for that with entity system architecture. Sorry. Another thing which is actually close to it is querying. If I would like, here I have a scene where I have different things on it, right? And if I would say like, okay, give me everyone who has a bow, or who is dying, or who is yawing, or who has a weird cap, right? This is also a little bit more complicated doing just with Unity, because then you would have to traverse the whole scene and actually see if components are in there. Maybe it's actually just a logical field on a mono behavior, so that would be really complicated. With entity system approach, we have a really easy way of querying the state. Then, I don't know about you guys, but for me, the most nice and important thing to do is actually deleting code. I love it. If I can delete code and the game still runs and really nicely, then it's the best thing that I can do. It's like what makes my work fun, in a way. The problem is, again, with Unity, if you have mono behaviors on prefabs, you might get these guys. You will definitely get these guys, because game objects are tightly coupled to the mono behaviors and back and forth. So therefore, if you delete those, you will miss them here, and so on. Again, this is something which we can address pretty easily with entity system architecture. So how does one simply implement entity system for Unity? Before we answer this, I would like to ask Simon to make a quick demo.
Thanks. So before we dive in and see how we actually implemented entity system architecture, be careful.
Sorry, I thought it would be a wall. It's not. Sorry.
I need you. I want to show you a little example project before that. So because we're going to see some code later in the presentation, and this code is taken right from this example project. So we all have the same idea. So I go to Unity real quick and show you what we got. So it's a really simple example. So it's a kind of Candy Crush type of game. In fact, it's even better because it's not matching 3, but only 1. So if you click 1, you also already get points. That's awesome. So you only can win, you cannot lose. So, and if you can see, we have 2 different kind of bubbles. Let's call them bubbles. So these ones, if I click them, they're interactive. It means they despawn if I click them, and you get score. And then they fall down. In comparison, these ones, if I click them, nothing happens. And they don't move as well. So they're not movable, and they're not interactive. Then we have the score label here, which always shows the current score you have. So again, really simple example. I guess all of you can put this thing together in a few minutes. But the important thing is not what we've built, but how we actually build it. So what is the most basic thing you need to describe data in your game? In our case, it's a component, similar to components in Unity. So if we take a look, where's the clicker? Awesome. So we have a position component here, which is just describing a point in a 2D space. So we have an X and Y field, and we're implementing the I component right here. That's just an indicator for us that you actually want to build or create a new component. So if you take a look and compare this to mono behavior, so components in Unity, the first thing you see, we don't have any methods. There's no start, there's no update or anything, and we don't inherit something, we just implement iComponent, so we don't get hidden state from other hierarchical stuff we inherit. So it's just plain data, and that's the really important thing. So we really want to separate the data from the behavior. Another example would be a game board element component. So in the game you just saw, everything is a game board element. In this case, again, we implement iComponent, and you see no methods, and we don't even have fields. The fact that something has a game board element means, so you are a game board element, that's already data enough for us. In Unity, you put the components and mono behaviors on game objects. And yeah, by the way, the library we're building is called Entitas, so every time I say Entitas, I'm actually talking about the library. So we're not putting it on a game object, we're putting the components on entities. So entities are basically just a container for components. You can add components, you can remove them, and you can replace them. And it's really easy to create one. So here we're just creating an entity, and then we say, you are a gameboard element by just flagging it with gameboard element component. We add a position, and then we add a resource that we actually know what sprite to render later. And we're creating a blocker here, so these things that are not movable and not interactive. So it would be really easy now to just create the other type by just saying, is movable true and is interactive true. So it's really easy to compose your objects in your game. And what you see, the pool, what's the pool exactly? So the pool is the place where all your entities live. So you create entities through the pool and you destroy them. And the pool is just managing their life cycle, and you can get all the entities out of them. Or even better, you can get groups. So groups are just subsets of certain entities in the pool which fulfilling a certain rule. For example, everything that has a gameboard element and has a position. So that's a rule. We call it matcher. A matcher is a filter description. And that's a really efficient and powerful way to get really quickly all the entities that match this filter description. And for example, you can see we're asking the pool for a group with a matcher all of gameboard element and position. So we get all these things back really efficiently. And there are also other matchers like any of, none of, and you can compose them. So there was quite a bit of information, so let's just step back and take a look of the whole picture. So again, we see the pool where all the entities live. And if we take one entity and zoom in, we see it's just a set of components. And if we zoom in further into the component, we see it's just plain data. And then we also see the groups again, which are subsets of certain entities in the pool, which fulfilling a certain rule. So entities could be in multiple groups.
Right. So if you think about it, what we described right now is just the state. And we'll like to think about it like the matrix, where you just see the data. You just see everything which is inside of your game. If you would pause the game and look at the pool, you see everything, which states to direct contrast to object-oriented programming, if you think about it. Because in object-oriented programming, what you normally do, you create classes which encapsulate state. And you create private fields, and then you have methods which work on this local state, encapsulated state. We have lots of information hiding, encapsulation, cohesion, which works nice until you have to introduce a new feature. And then it becomes a little bit ugly, because we took all of the information and put it in small boxes, which is really nice. And then some game designer comes in and says like, okay, I would like this to do something completely different. So you would like to, you would have to actually break all the boxes or try to extend the box, put something at the side, and so on and so forth. And this becomes really, really complicated. So scaling horizontally or actually exchanging stuff, adding features, is much simpler if you have this kind of global state, right? We spoke about state. What about behavior? Because a game lives through behavior, right? And I'm a pretty weird person. I think personally that games are just interactive simulations. I think there are lots of people which would strongly disagree with me. They would say games are art, games are magic. For me, I'm a programmer. For me, it's just an interactive simulation. I start with a state, then I transform the state over time until it's game over. Right? And with interaction, you could, basically the player can influence how the simulation will go from now on. So to perform this state transformation, state changes, we have something which we call systems. And we have two types of them. So a start system. Start systems are normally there to create state. So for example, you would like to load a level from some certain description into a pool. And then you create state with a start system which is executed only once. Then we have execute systems, which are executed on every tick, on every frame, which will then transform the state from one to one, making the simulation work. One important thing, however, is that we decide not to put state in the systems, because we would like to have this global state. We would like to be able to stop and actually just look at the pool and understand in what kind of state we are right now. If we would put data into the systems, then we would have this information hiding. Here's an example of move system. And you see here an execute method. So it's an execute system which will be executed on each frame. And it only does one thing. It queries the pool, says, give me all the movable entities. And then we just iterate through the entities and basically just take the position and add the move speed to the position. With this kind of approach, it is also easy to implement single responsibility principle. And therefore, if you do this, it is really easy to decouple features, turn them off and on, and so on and so forth. If we have this kind of small systems, we put them in a chain and then just execute them through on each tick. So we have a chain of responsibility. Each system knows what exactly it does and will do it if there is some work to be done. If there isn't, it won't be. So one of the important points also in the system design is early exits. If you see there is no work to do, just exit directly. This is from the Match 1 game. This is basically all the systems that we had to implement to make this example work. And it's also pretty simple to read it and understand what exactly going on in the game and also in each system. As they do only one thing, so you can name them explicitly so that you can understand. Now, we also mutate state on changes in the group. As we mentioned, we introduced groups actually just as a performance optimization, to just say, don't give me all the entities, give me only the entities which have such and such component. However, we saw if we would add an observer on this group, then we can do something like key value binding. If an entity gets added to the group, we know that it changed its state, so we can just grab this entity and execute something. Here is also an example from the Match 1, where we update the score when the entity with a score component have been changed. Therefore, you have a pretty much reactive way of updating your UI without having some connections from your model to the views and so on and so forth. It works automagically in a way. We went a little bit further because I already said like the systems are executed on each tick, right? But sometimes you don't want to execute a system if there is nothing to do. And we implemented reactive systems so that they can just react on changes. Imagine you have, for example, 100 units, only 10 of them have moved. So we would like already in the execute get only the entities which have moved so we can apply the speed or movement vector or whatever. Here is an example of random position system from the match 1 example. So what we basically say is, OK, we monitor this group which applies to this matcher on entity added. We will change the transform of the view. This means that if a position have changed, we will adapt the transform. And also if we decided to change the view, so we actually decided to replace a game object and put it a new one, it will also directly get the right transform. Now Simon will speak about optimizations.
Thanks. So a really important thing for us was to have a really performant and optimized framework to work with, and we did a lot of optimizations. We have a lot of internal caching wherever possible, and we use pooling for entities and all this good stuff. But I want to point out 2 special things. The first one is components. So we were asking ourselves if we should make them mutable or immutable, meaning immutable, once they are created, you cannot change the data again. So what you have to do, let's say you have an entity and you have a position on it, and you want to update the position. What you have to do is you have to remove the old one, create a new one, and put it on top. So the old one is just thrown away. So what we can see here now, that's the Unity profiler. And you can see these yellow spikes. So these yellow spikes, probably you know it, it's the garbage collector kicking in. Because, as I said, we have to remove the old position, and this thing is just garbage collected. And that's definitely a thing you want to avoid in your games. You don't want to have the garbage collector kicking in that much. Because you will have frame drops or something like that, and that's a hiccup in your game. So what we've done is we designed the whole API as if we would actually work with immutable data, but under the hood, we're just reusing the components. And the result was we got rid of all the garbage collection, and we have a really stable and smooth simulation. The next thing is how we actually store the components in the entity itself. So a really easy approach in the first version was just to take the component and store it in a dictionary, and the key was the type. So you get a similar API like you know it from Unity with game object get component, and then you pass in the type. So that was really a nice API, and it was nice to use, but then I was trying to back up the components in an array, and it turned out to be much, much faster. But if we compare the API from these 2 approaches, in the top, you can see with the dictionary. So, for example, we get entity, get component, position components, as you know it from Unity. That's nice to read and nice to understand. But if we compare it to the array approach, there's this weird 5. What is it? That's in fact the index where we store the component. So each component has its own index in the array. And we weren't really happy with that because you can make a lot of mistakes there. It's really error prone, so you could possibly pass in a wrong index, or here you can see we have to cast it to something. Maybe you cast it wrong. So we weren't really happy with that. So on this awesome graph, you see the API awesomeness and the performance. So the dictionary had a really nice API to use, but the performance wasn't that great. On the other hand, the array has a really, really good performance, but the API just sucked. So, and where we actually wanted to be is right here. So we want to have the power of the array and the speed, but we wanted to end up with an even nicer API. And I'm really excited about that one because we actually achieved that with code generation. So let's talk a little bit about code generation. You don't really have to read this code. It's just the amount of code you had to write to replace a position in a certain way. So the intent is not really clear. You have to really read to understand what it's doing. And somehow in the end, we're replacing something. And there are a lot of places where you could mess up. Maybe here, we're casting wrong, or you pass in a wrong index again. So what if we could just write what we actually want to do? And what do we want to do? We want to replace the position, something like this, entity, replace position, and then with x, y, 10. So that's what we want to do, and the code generator enabled us to write that kind of code. So that's actually the result of after we're using the code generator. And I think that's pretty awesome because the intent is really clear, you cannot mess it up, and it's easy to write and really easy to read. So because it's so easy and great, I just want to give you a little demo of that. So therefore, I open just this example project. So we have an empty new Unity project, which only has the library, the Entitas library inside, and an empty game controller. So let's just create our first component and see how easy it is. So we create a new script, and let's say call it position component, and open it. So the first thing we do, we just remove everything we don't need, which is basically everything. And then, again, we're writing a component, so we implement iComponent. And let's create the two fields, or since it's Unity 3D, let's do a Z as well. Sorry. Oops. All right, so that's basically everything you have to do. Again, we don't have any methods, or we don't implement any, inherit anything. It's just plain data. So if we go back to Unity, we can see there's an Entitas menu entry up there, and a few things, but we're interested in the generate button. So we just hit that thing, and as you can see here, a new folder appeared right here. That's where we put the code. So you can specify where to put the code, but at the moment it's just in the root of assets. And two files got generated. First, a position component extension, and then another class where all the bookkeeping is made, so the indices are mapped to the components. So let's just open the game controller and use this component. So first of all, we need a pool to actually create an entity. So let's do that. So we say new pool. And the pool accepts the total amount of components, so it internally can manage how to create an entity. And this is also generated. Comp IDs. So now we have a pool to start with. Now let's create our first entity. Let's say E equals pool, create entity. And now we can use the positioning component we just created. So we can say, for example, add position, and then 1, 2, 3. Or remove position. Or let's say we want to get the position value, we can say E position.x. So I think that's a really nice and readable API. So you cannot get it wrong, and the intent, again, is really, really clear. So it's really easy to create this. In fact, it was so easy and fast. Let's just create another one. A movable component. And again, remove everything we don't need. Whoops. Implement iComponent. In this case, we don't need any fields because we just want to tag something, you are movable. So already done. So we go back to Unity, and again, we're looking for the generate button. And as we can see, there's another class generated now. Let's use that. So we can simply say is movable equals true or maybe false. And we can also get it. Really easy to read, really easy to write. I think it's awesome. So what is it doing here? It's just adding the component under the hood or removing it. Yeah, I just love this API. All right. So how do we actually do that? As I said, every component implements iComponent, so it's really easy for us to go through the whole assembly and get all the components, and then we can inspect with reflection. We can get all the public fields, and based on that, the code generator generates different output. For example, the movable component had this is movable syntax, whereas the position had add and remove and stuff like that. So it's the code generator smart in generating different output based on the component. And we started with a simple approach, like maybe you know the C# extensions, where you can simply add public methods to classes. But this approach is kind of limited because you can only interact with the public API of a class. And we wanted to have something like this position thing, which is basically a getter. And for that, we tried out partial classes. So if you're not familiar with partial classes, you could just start the normal class in a file and mark it with the keyword partial. And then you can go ahead in a different file and write additional logic for this class. And you can have even more files where you can just add functionality to this class. And in the end, the compiler puts everything together into one single class. And the cool thing about that is we have access to all the private fields. We can add getters and setters and all this stuff. And that's how we actually did it. Yeah. And if we don't like the entity system or whatever, one thing to take away is code generation. It can really speed up your workflow and save you a lot of time writing stuff you don't need because the computer's just much faster in writing stuff you write over and over again. So we actually use code generation in different areas like asset bundles or localization. So if you want to know more about that, we have some really cool things to show you. Yeah, the next thing is visual debugging. So we have this whole framework now with all the features and the speed we wanted and the nice API. But when you use it and you play it in Unity, you don't see any game objects and you don't have mono behaviors. So the hierarchy is pretty empty. And as a Unity developer, you're really used to clicking on the game objects, inspecting mono behaviors, and changing values at runtime, which is really powerful and really convenient. So we wanted to have the same power and convenience with Entitas as well. And that's the job of the visual debugging tool we've built, which is exactly doing that, integrating Entitas seamlessly into Unity. And I'd like to give you a demo again. So let's just open the match 1 again. All right. So if we take a closer look at the hierarchy, we can see the usual suspects like camera, game controller, and stuff like that. But we see also the pool. And if we click on that, we can see we have currently 75 entities. We have a few groups that were requested at this time. And we can also unfold that one, and we see all the entities created. So that's really nice, and they all have the components in their name, so it's really easy to just search for them in the search field up there. And if you click an entity, you see all its components. For example, this entity I selected is a game board element. It's interactive, it's movable, it has a position, and so on. And we can change the values, and we see changes in the game in real time. That's really awesome. And we can also destroy this one. So I just delete it. And we saw we also get a score because everything is reactive. The reactive systems noticed something got removed, so that's obviously a score for us. So if I select multiple of them and I delete them, I get score for them. Another cool thing, and the power of entity systems is an entity could be anything. So depending on the component it has, it's representing an object in your game. So we can easily change that. Let's just maybe take this blue one in the corner there. Oops. And if I remove, for example, interactive and the movable component, if I click it, nothing happens. And if I remove that one, it doesn't fall down. So basically, it's a blocker now. So and it's even better if we change the sprite. Now we just change the thing while the game is running from one thing into another thing, which is really hard to do with object-oriented approaches, where something is that thing once you created it. And here we can change it back and forth. So an entity could be anything, and you can change anything to anything, basically. And that's really awesome, I think. So that's the state and the data which we were visualizing. But what about the systems? So the behavior. We see here, we have also a systems thing here. So let's click on that. So we see we have a few start systems and a few execute systems. A few of them are actually both combined, so that's why they don't sum up to total. And you also see them listed here, and they are ordered by execution time, which is pretty nice, so you can focus on optimizing the slowest systems. And let's just do some stuff. And here you see which systems are slow or fast, and you also get a little visual representation in this graph. So that's really cool. And if we go back to the data, just one thing how easy it is to change stuff. I could also change, for example, the grid size. If I go here, and now we have a 3x3 grid. Or we can go crazy and create a 50x50 game grid.
Take a while.
It takes a while, so maybe we should update the camera. What was it again? Something like that.
22.
Awesome. So, and everything just works, and we can see how it performs with the system profiler. And if you can see, if you don't do anything, it's basically at 0. It's awesome. All right. Thanks. So I guess maybe you liked what you saw, and if you do and you want to get your hands on it or want to see, want to try it out, it's open source. It's on GitHub. You can just go to this address. There's a wiki and README. It's explaining everything, and there are also 2 example projects. So the match 1 and also a different one, so you can really see how these things work together.
Yeah. So I would like to give a short recap, basically, what we talked in the beginning about the pain points that we had and how you can address them with entity system architecture. Testability is pretty easy because you just have to initiate your state, execute one system or multiple systems, and then just look at the state afterwards. So it's really easy to test. It's really easy to work in test-driven way. Code sharing also, as we use only standard C# stuff, it's really easy then to run it on backend. Codependent logic, basically a system gets all the units, and then the system can then just distribute, say, you go here, you go here, you go here, you go here. So we have this supervisor idea directly implemented with the systems. If you would like to have more fuzzy one, then you would just have to implement your system in a way where it just improvises as if it doesn't know where the other units are, but it's much easier to do if you have more data than if you have less data. Querying, it's basically just groups. Right? You can ask for stuff which is logically represented, and we represent everything logically. And therefore, it's really easy. And deleting code, if you follow the single responsibility principle, and it's really easy just to comment out the systems. Actually, in the editor plugin, you can also directly stop a couple of systems and see how it will affect the game when you run it. Right. So we also get some advantages from this. It is really straightforward to achieve deterministic behaviors because everything is written in code. The chain of responsibility is written in code. Everything is data. And if you also write tests, for example, even if you see that something is non-deterministic, you can just describe it as a test, run it, debug it, and then you can find the points in your code which are non-deterministic. If your code is not testable, this is really hard because you have to reproduce it in a real game. You can't just isolate the behavior and be able to pinpoint these problems. Simulation speedup is also simple. As we tick along the system on every frame, what we can do is basically just wrap them in a for loop and just say like, okay, execute them not once per frame, but 2 times, 4 times, 10 times per frame. And then you have a speed up of your simulation. What we also sometimes do is having headless simulations. I already mentioned that we validated the battle on the servers, and this is basically headless simulation. We had battles which took 5 minutes on the server. In headless mode, it took just 2 seconds or less than 2 seconds. What you have to do is basically just remove all the systems which do rendering and just keep the systems which transform the logical state. Pretty easy to decouple. Save game to backend is also simple if you have group observers where you say like, okay, if my position changes, and I don't care what it is, it can be a building, it can be a unit, whatever, I will just communicate it, notify me, and I will communicate it to my backend. Very simple stuff already baked in just in this architectural thinking. And last, but in my opinion, not least, at least for me and Simon, actually it replaced all of object-oriented design patterns. We have this model of thinking that everything is the data and we just transform the data. And then it removed lots of abstractions that you actually end up with if you do stuff in object-oriented approach. So, thank you very much. Do we have any questions? Yeah, we have a mic running around here, so there was one guy with a Redis shirt first.
Hi, thanks for the great presentation and making an open source. I have a question. If you have like an hotspot component or a collider component, of course you have to interact with the Unity values, because if you change the, let's say, the size on the hotspot component, then also the Unity collider has to update, right? Where do you put this code? Do you put it in the system or do you put it in the component?
So usually, the thing is, there are also other related stuff which Unity is taking care of. For example, physics is another topic. So usually we try to have everything in the pool, and systems modifies things. For example, also this component. So we try to put it. We want to abstract it in our own components, and then we have systems which are updating the Unity components, like the game, game object, for example, which is for us just a view. with the sprite renderer, we update its position through a system, but the position itself, we store it in the pool in a position component, for example. Or the physics I just mentioned, well, that's another case, but what happens there is Unity already has a system for calculating physics, for example. So we don't have to implement it ourselves. So we're not going this way from our systems to Unity, but we give Unity the responsibility to maybe calculate the systems, and then we could have a system that is updating based on the Unity results, the entities and components in the pool. So we sync it back and forth.
So you're putting it in a separate system, the syncing
so
essay.
yeah, exactly.
Yeah,
so
that's cool. Yeah.
for example, physics is a really nice example where we sync back. So usually in an ideal case, maybe we would implement it ourselves, but why? Because Unity already has a really good solution for that. So it's just easy to sync it back, the results, and it's like an external system from somebody else. Yeah.
Thank you very much.
Welcome.
One here, and then one here.
Hi.
Hi.
There was one thing about your presentation that I didn't really get, and that was about immutability. Do you still use immutable objects under the hood, or how does that work?
Yes. So in an ideal world, we would use immutable components. But as I said, and as you could see in the profiler, that leads to all these spikes, so the garbage collector. And we wanted to avoid that. But we still have discussions about that, because you get a lot of benefits from immutable data, especially if you go multi-threaded or something like that. But at the moment, under the hood, we're reusing these components and we're changing them. But as I said, the API gives the impression as if you would work with immutable data. So that's why we have this replace and stuff like that. So your mindset should be, okay, that's immutable, but under the hood, as an optimization, we just reuse it.
Yeah. So have you thought about using immutable data structures like they're used in functional programming languages?
Yeah, in the beginning it was all immutable. We changed it afterwards, and that was a kind of bold decision because we wanted to go for immutable data. But since we're in an environment where there's garbage collection and stuff like that, we wanted to, especially we're doing mobile development and on phones with limited sources, you would definitely want to avoid that.
Okay.
As a matter of fact, we have different ports for different languages, and for example, we started with Objective-C, and Objective-C it was immutable because you have ARC, automatic reference counting, so you don't have garbage collection. Therefore, it is not a problem. And I also wrote a port in Swift where it's also not a problem, but at the moment where you run in an environment which is garbage collected, you don't want to just emit data, you have to transform it. Because otherwise, if you're just emitting, garbage collector will say, oh, garbage, great, I have so much stuff to do. Yeah. And you don't want to have it on every frame.
Okay,
right?
Thank you.
Thank you. Any more questions? Yeah, yeah.
Hi, my name is Stepan, software developer like yourselves. I really like the Entitas,
right? Yeah.
Entitas, especially that you have actual abstractions for a system which Unity doesn't have. Because Unity is in a way entities systems framework is just not as obvious as in your case. Anyhow, I have a conceptual question. I have seen how you kind of mirror your pool of entities onto Unity. You kind of project pretty much your own simulation onto the Unity. And I've seen that, at least in these examples, that you create lots of things in code. So it's kind of, at least I have an impression of Entitas as a programmer tool. But don't you think that by creating this kind of own simulation parallel to Unity, you steal the right of the designer who normally works with a scene and hierarchy? You kind of take that work from a person who's normally responsible for adding component and designing entities and make a developer happy and put that work in the wrong hands.
Should I?
Go ahead.
That's a really tough one. But basically, if you think about it, we do the simulation in Entity, and we would like to have logical representations. The designers can still have their prefabs. The designers can still define the levels in Unity, and it's all fine.
And it's just data, so no behavior.
But for us, the most important thing actually for us in Entity system, we would like to separate behavior from data. What also the designers would like, they would like to change data and it should reflect in the behavior, right? So still in Unity, you could describe everything in your prefabs, in your game objects, which will just be caught up by the systems and which start transforming them in a way that it starts simulating. This is actually pretty fine. And I guess you also you have like 3 game designers on your team which actually work with.
So they actually work with Unity and these tools and building levels and stuff like that. And what I do in the end, I transform this into entities and components. So I get the benefits of what you just saw, but they can work as they are used to. Maybe there are some games maybe where it makes sense to go for the Unity approach, but in simulation games, for example, Clash of Clans types of games, or let's say match 3 game like Candy Crush, it just fits really well, and you get benefits from test-driven development and stuff like that. Maybe a 3D shooter, you could argue maybe that Unity tools are better suited for that.
We don't know yet, so we didn't implement a 3D shooter yet, so when we do, we will tell you. All right, next question. Yeah.
So it's about immutable objects again.
All right.
Because we've heard a couple of examples of why it's difficult to abstract this away from the API user. I wonder what advantages drove you to do it anyway?
The whole idea of reactive systems and this observing of the groups. Because if you would imagine you would like to change a position, you could just get a position component and just exchange the x from 5 to 10. Then no one knows that you actually changed position logically, right? You did it directly, and there is no mechanism in C# which lets you observe a change of an object or a struct. What we say when you replacing the position from 5 to 7, and we will get this event, we will get notified. Everyone who would like to be notified on position change will be, and therefore we can create this reactive approach. That's also why stuff work in the Unity editor. You can just move the position. Internally, we basically exchange the position even before we just actually apply it and then reapply the component. But the systems get notified and they know, oh, new position, let's move him. And this is why we need immutability, but we fake it. Yeah. One more question over there, I see. And also, who wants to go first? Sorry.
I'm wondering why, I guess you already tried that, but what was the limitation of extending the game object class?
It's too heavy.
But they're all game object either way.
Yeah, but like the point is, I would like to have lots of data. I could have, for example, in a simulation game I worked on, we had like thousands of entities. And I don't want to have thousands of game objects because they have all this baggage which is needed to render stuff. But and basically, if you think about it, game objects are, in a way, the most important thing is actually visualizing on screen. That's why you have also transform component baked in. It's a component, but it's really baked in the game object. So even if you have a logical game object, you still have a transform which is 0, 0, 0, which feels weird, but it's understandable because you would like the main objection of a game object is to be something which is rendered. We would like to just have logic. without any behavior, just represent the matrix, the
And
greeny
we don't
thingies.
don't want to be coupled to Unity because for the reasons of code sharing and running it on a server or running tests, without Unity test tools, which we didn't have back in the days when we started with that. So that's just a really nice way not to use Unity stuff. That sounded weird, but it's good. You have benefits for example, testing and code sharing. And game objects, you destroy that freedom then and flexibility.
Thank you.
Now,
Yeah, so you did an amazing job, guys. Really great, and to see Entitas. We've been building
Thank you very
a
much.
pretty similar framework over the past few years, and we're planning on making it open source, but you were faster.
sorry.
And,
Sorry.
It's okay, it's great, it's really great to see it. I was just wondering whether you have some kind of event management in place, because we've been making the experience over the past few years and games we've been making that most, if not all of the systems don't need an update loop. It's basically, if there's a system that needs an update loop, it's mostly some kind of physics system that, if you have a real-time game that updates the position, and that's basically it. Everything else is just event-based. And I was wondering whether you have been making the same experience, or how do you handle it? Do you just set flags on components and other systems react to these flags, or how do these systems communicate to each other in your case?
Yeah, so you maybe remember the reactive systems. They actually do that thing. So without the reactive systems, we started flagging stuff like you need an update or something like that, which is kind of like an event, but yeah, with a component. And the reactive systems eliminated this need for these flag components. By just changing something, the reactive system will process it. So if you want to communicate or have some kind of events like this, you just change the component, and that's already like, or you use the group observers, where like in the example with the score label, where it just observed a group, the measure was score, so you have a group of scores, there's just one score, but if that thing changes, I can execute some methods, for example. So
the systems are basically just listening for changes in any of the component values, in any of the group entities, and reacting to these changes.
In the reactive systems, yeah. In the normal systems, you just do whatever you want to implement.
What we also do is, why reactive systems are also pretty cool, is actually that we collect the changes over the frame. So therefore, if you have, for example, multiple systems which change a position, we don't react directly on the change of position. We react only like on the position in the chain where this reactive system is executed. Yeah. So you kind of collect changes over the whole frame, and then you see like, I have work to do, so I will do something, or there is nothing new, then just skip me and go on.
And what about, just to follow up on that, what about changes or events that are not entirely database, something like a collision just happened, or a user clicked a button that's basically something that won't change anything in any component data, but you have to react to it anyway?
Well, you would have to basically reflect it as a component. We then say that, for example, if you have an event listener, you just add an event listener, which will be a pretty simple mono behavior, which will just create an entity with a certain component. For example, in my simulation, I work now on a different simulation game, and we have our touch interaction, which is just about interacting, zooming, and pinching, and so on and so forth. It's also done with systems, and we can easily, for example, remove inertia if we don't like to have it. We can add inertia. We can remove elasticity. We can add elasticity, and so on and so forth. So therefore, we just create components once, and then the systems will logically do their job.
Okay, thank you.
Yeah. Question over there?
Last one.
All right.
Last one. Then, sorry.
Sprint.
What do you use for code generation? Do you use something like Russelin, or do you have your own code written that executes to writing to a file?
So we have just an own solution, which again just scans the assembly for I components, and then with reflection we can get all the public fields. And based on that, we just create files.
So you have a problem that if your code doesn't compile because some
that's right.
changes,
Yes.
because you have a merge or something like that?
So if your code doesn't compile, you cannot really recompile a new assembly with your new components, so you cannot generate. So you always have a running version in order to
Okay, thank
generate.
you.
Yeah, welcome.
Last one, or
Yeah.
there was one in
Alright.
the back, and I think it's
One last
one.
question. Oops.
Hey guys, thanks for the presentation. I have a short question. Do you feel this system shouldn't be used in any other types of games, or where do you feel it's falling short?
So there are certainly games where it makes a lot of sense, like this game, for example, or Clash of Clans type of games. And I guess there are also games where it doesn't make sense. So that's always up to you in the beginning to see your requirements, what you have, see the requirements and technical.
But do you know some situations from experience?
I personally actually right now even write apps with Entitas, which is like completely something not even games related. It's then not with systems, but actually just using the state part because I like the flexibility. And it's
Maybe a 3D shooter, I don't know.
like we haven't worked on 3D shooter yet, for example. We don't know.
Because
Maybe
Unity
that-
gives you a lot of cool things, like, as I said, physics and other hit collision, collision detection,
As
stuff
far
like
as
that.
I know, I think EA also have their entity system approach also in their 3D shooters, but it's always hard to say because like entity system and entity system can be really different. It's like really hard to know who understands what under this fuzzy term. That's why we try to, like from the ground up, just explain what do we understand under entity system and what it is for us. So,
Okay, thanks.
Welcome.
thank you.
All right, thanks, guys.
Thank you.